Hey, this is James D. Kahn, and we're back for another tutorial. And last time we worked on our terrain shader, and I know I had mentioned that I was going to show you how to do some terrain collision detection. And so that's what we're going to do today. Right now, I think, so the current state of the project is we have a terrain, but the slime, he can't walk on it or anything like that. So what we're going to do today is add some basic collision detection like this, so that the slime stays on top of the terrain, and it kind of follows the contours of the terrain. Now, what we're going to be doing today is, so we're going to be achieving this today without using any physics. Now, usually on projects, when I do something like this, I use Bullet, or I use a physics engine. So with libGDX, usually that would be Bullet. Bullet has a height field terrain shape, which is really nice to turn your terrain into a physics object. But for today, you know, we always like to stick with the basic stuff first, and I am thinking of doing a kind of introduction to Bullet separate series on libGDX. But for now, we're just going to be doing a basic collision detection on our terrain with no physics or anything like that. Yeah, this is what we're going to end up with, and let's get started. So the tutorial will be pretty quick today. And that's because, thankfully, this has already been done before, plenty of times. And one in particular example that I've used before is the Thin Matrix videos. Thin Matrix has a lot of great OpenGL videos, and he's working in Java as well. So I was able to take, you know, this same approach that he uses in terrain collision detection and from this video, and apply the exact same approach to our libGDX code. Minus a couple very minor changes. So what I'll be doing today is more just implementing the technique from this video in our project, and just a couple tweaks to make it work with libGDX. So if you want to know more about the math and the details of how this works, I would highly recommend watching this video, which I can include a link to afterwards, as he goes into more detail than I intend to, because I don't want to reinvent the wheel and just say the same thing over because he's already said it. But I will, you know, we'll talk about it a little bit, and I've added some comments to the code as well to try and explain what's going on. But I highly recommend this video if you want to have a better understanding of what we're going to do today. Head over to your terrain class, terrain.java, and we're going to create a new method here. A new abstract method that will implement in our height mapped terrain. And it's going to return a float value. And so this method is going to return the height at a world coordinate. And it'll take in the world X position and the world Z position. Okay. And now let's head over to our height map terrain, because we're going to need to implement this method now. So I hit Alt Enter and implement method. Here we are. And so we'll get started here. And as I mentioned, so this code is almost one-to-one with Thin Matrix, minus a couple. I've made a couple small changes. One is for performance reasons, and I'm going to bring those over now. So we have a couple vector 3s that I'm going to add to this height map terrain, and I'll explain what these are. I think so. You've kind of seen something here before: corner 00100111, and we have the same thing going on here. I'm just creating these static vector 3s for reusability, because we're going to need to reuse these over and over and over again. And just for performance reasons, you don't want to keep creating a new vector 3 constantly. If you can reuse it, that's ideal. And so that's what we're going to be using these for down the road here when we get into this get height at world coordinate method. So we're going to first start off by getting the world position of our terrain, and we can do that by using the transform from the terrain's model instance. And then we can do get translation and put in C00, which is our top left corner, or will represent our top left corner of the terrain. For now, because we're going to reuse this this C00 a couple times. And now what we need to do is we want to convert the world coordinates to a relative position on the terrain. And we can do that by negating the world positions. So if we take a look here, let's get, so we want terrain X, and this is going to be the relative position. We take the world X coordinate that was passed in, and we minus the terrain's X position. And we'll do the same with terrain Z. So if we look at this here, and say the terrain is positioned at 100, 100, 100x, 100z. Let's say that's where the terrain is at in the world. It's not at 0, 0, 0 in this example. Now we pass this in, and once we get here, let's say the character's at 120 on the terrain and in the x position. So we're going to take that 120 minus the world position of 100. That's going to leave us with 20, which is kind of which would be the relative position on that terrain. We don't want to work with the world coordinates here. We only want to work with coordinates that are relative to this terrain. So in this way, what we can think of is that the top left corner of the terrain is always going to be at 0, 0 in the relative terms of when we're inside of this method, working this out. The next thing we're going to do, and actually, so I'm going to add some comments as we go. There we go. Okay. The next thing we want to do is get the size of our grids in the terrain. And I'll show you what that looks like in a minute. So we'll take the size of the terrain, and we're going to divide it by the width of the terrain. And now the width came from the size of our height map in this case. And if we take a look here, let's try to visualize this a little bit. And to do that, we can head over to our, we're already in our height map terrain. Let's make a couple little changes. You don't have to do these changes if you don't want. I'm just going to use this as a quick demonstration here. So I'm changing our terrain material over to GL lines. And I'm going to go over to where we render our terrain. And just make a little call to OpenGL here, just to make the lines a little more visible or easy to look at. Let me just launch this. And again, like I said, this part, you don't have to do this. Just want to use it to take a look at our terrain here. So I had mentioned grid size, right? And so if we take a look, you can see now, very apparently, you can see these grids. And that's what we're going to be talking about in this method when we're talking about the grid. So if we move over into Microsoft Paint, I've just made a very quick little image to try and help explain some of the terminology that we're going to be seeing in the code. We have our grids here, and you'll notice I've made some changes here as well, because OpenGL, as you're probably already aware, uses triangles. But if you see here, we're looking at a bunch of squares, but in reality, what we have is each of these grids are actually sliced into two triangles. And so to visualize that, we have the line coming through the middle, and you can see the two triangles makes up each grid on our terrain. And so we have our corners. So that's going to, this just shows you those vectors that we are going to be using, those static vectors, the C00, C for corner, C01, 10, 11. So that's what those vectors represent, is going to represent the corners of each grid. So the idea here, the goal, is to figure out, one, which grid are we currently standing in on the terrain, and then two, figure out, are we in the top left triangle, are we in the bottom right triangle? Because if we just go by the vertices, which is represented by these red dots here, if we just go by the vertices and say, oh, hey, what's the height at this corner, what's the height at this corner, you could do that. But depending on the size of your terrain, if your vertices are really far apart, and let's say you're a really small character and you're right here, well, the height could be very different in the spaces between the vertices. So that's why we want to kind of break this down and figure out not just what's the height at one of the corners, but if I'm standing right here in this grid, what is the height at this point on this triangle? Okay, heading back to the code, I'm going to add in a comment here. And then next up, we need to determine which grid square these coordinates are in. So we're going to have two integers. And we'll divide that by the grid square size. And we'll do the same thing for the z. Okay, so this will give us the grid coordinates, an integer that we're currently in. And next, we're just going to do a quick validation. We just want to make sure that this grid X and grid Z are valid and they actually fall on this terrain. Oops. Okay, I'm just double checking here. Grid X greater than or equal to the width minus 1. And grid Z the same. And then we check if we're less than 0. Okay, so yeah, if any of these are met, then we're not on this terrain grid, or these grid values don't fall within this terrain, so we're just going to return 0 in that case. So we would see this would get returned here if I take the slime and walk him off the grid. But we want to catch this and return something. Otherwise, we'll likely end up with an error down the line. Okay, so the next step is to determine where on the grid square the coordinates are. Or basically what we're trying to figure out now is we're trying to determine which triangle, which of the two triangles on this grid square do we fall within. And for that, we're going to use the modulus. And then divide by grid square size as well. And again, same thing for the z chord. Okay, so again, if you have any questions about this stuff, I recommend checking out Thin Matrix's video. A lot of this is one-to-one, just a couple of small changes here. So next we're going to define our height float that we're going to be returning. Okay. That should be right. Okay, so this is where we're determining, are we in the top left? In this case, let's see here. So this will be the upper left triangle. Else, let's just get these conditionals in place. Okay, so next we're going to need this method here. You saw I wrote barycentric, and so I learned about this from, I mean, it's used in a lot of things from what I learned, but particularly I learned about this from the Thin Matrix video. And I'm just going to go ahead and bring over this method that we're going to need. And it's taken, like I said, it's taken exactly from the Thin Matrix video. But the idea again here is to determine where now in the triangle that we are. And for now, I'm just going to put this method right down here below. Probably we want to move this to like a utility class. But for now, this should be fine. And so we're going to pass here. So it takes in 3 vector 3s and a x and z position vector, vector 2. And so depending on which triangle we end up in is going to depend on what we send into this function. And to save some time, I'm going to bring over what we need here, and then I'll do a quick explanation. I will not be explaining how barycentric works because I don't fully understand it myself. So if you want to look it up, you can. For me, it does what I need, and that's all I really care about. And then lastly, we will return that height, and then we also have to include the height magnitude that we defined in our terrain class as well. Otherwise, the height won't be right; it'll be off. Now, this what we're doing here, what we're sending in, you see, we're calling this field.data, and if you remember back, field is this height field class that we actually brought over from the libGDX test class, or the libGDX test package. And that's actually what we're using to create our terrain. It's part of our height field. And what we're doing is we're actually getting the height data from that height field class. So this field.data is a one-dimensional array. Now, in Thin Matrix's video, I think he's using a 2D array of height values. So this part is a little bit different, just what we're passing in here. And if you're curious about why, what is going on here, this is how we're querying with a one-dimensional array. If we were using a two-dimensional, it would look a little bit different. But if you even look at the height field, part of the height field in this description shows you how to get the index within an array. So the index within this array can be calculated as, so you take the y times width plus that x value. And so that's what's going on here with the general gist of it. We're taking this, well, we say y, but in our case it's z times the width plus the x. And so all this is doing is retrieving the height data at this index location based on the grid x and the grid z values. And then we're also doing the corners, right? So we have the three corners in this case because we're working with the triangle now. And we're just setting these static vector 3s to the appropriate values for the three corners of the triangle, depending on what triangle we are in. And again, check out the video from Thin Matrix. I think he talks about it a little bit more if you want to look at that. And that should complete our get height at world coordinate method. Oh, and it looks like I had one mistake here in the code, which was a test to see if you were paying attention or not. So we want to change that equal sign to a minus here. And now if we come over to our main game class, we're going to call that method to get the height of the terrain and apply that to our slime. So we're in this process input method here where we're updating the slime's position. So yeah, we update the transform here, player transform. We set that to the slime. And then we call this get translation on the transform to just update the current position vector with the latest position. So right after this line is where we're going to start tapping into that new height method. So we'll call here float height equals, and then on the terrain, get height at the world coordinate. And so we can pass in the current position, x and z. And now we're going to update the current position's y value to equal the height. And then on our model instance for the slime, we're now going to set the translation to the that modified current position because we modified the height value here. And so that should now move the slime, apply terrain height to the slime. And let's try running this code. All right, I'm gonna press tab twice so I can get into this third person mode here and just take a look. And it looks like we're in business. So the slime is, is moving over the terrain. He's hitting the bumps. The more drastic the slope, the more kind of, it's going to look a little off because we're just querying, or sampling one position on the terrain. So it won't be perfect, but this is a start. Probably some interpolation, and there's some other things that can be done to clean this up better. But this is definitely a good start. And we're not falling through the terrain anymore, which is awesome. And like I said, normally I would use a physics library like Bullet for this. But if this is all you need and you don't need the physics library, you know, everyone's needs are different. This is one approach that you can use without having to set up, you know, everything that Bullet requires, which is quite a bit to get going with Bullet. And we'll do one other change here just to show another way to use this new height method, because you'll notice that I can move the camera underneath the terrain, which you know, isn't really ideal. So we can take the same height method and apply that to our camera as well. So if we head over to the update camera method, we can check the height of the camera, check the height of the terrain at the camera's current position. And we can check the camera's Y value. If it's less than the terrain height, plus we'll add some padding as well, so that we're not going to let the camera sit right on top of the terrain, but add an extra layer of padding in between the camera and the terrain. So if the camera's height is less than terrain height plus 10, then we're going to update the camera's height value to be the camera height, or the terrain height plus 10. And we run that. Okay, so now if I try to move the camera underneath the terrain, it shouldn't let me do it. In fact, the camera should kind of follow the terrain now. And you'll see that so right now my hand is not, you know, moving the camera at all, but you can see that the camera is automatically changing its height value to be above the terrain. And this is just, you know, I just wanted to show you this is something else. Another way you can use that same method for the terrain height. It has plenty of uses for it, including, you know, preventing the camera from going underneath the ground. So that's just one other use. And I think that does it for this tutorial video. I'm trying to keep it as short as I could, and hopefully this helps out. I know it's been a couple weeks since my last video, so I really wanted to get this one out there. All right, thanks for watching.